Welcome to part 2 of lecture 3 for Chemistry 312, Radiochemistry. This is the second part of the lecture on radioactive decay kinetics. The first part covered basics of the equations, and the second part we're going to focus on utilizing these equations, where we talk about mixtures of radionuclides, equilibrium, if I have a parent and daughter in equilibrium, but how much time does it take for them to reach equilibrium? We'll see that that depends upon half-lives. Branching, where we saw that certain isotopes can decay by two methods. We'll talk about parent, daughter, granddaughter, great-granddaughter, decay chains. This is all based upon the Bateman equation. We'll actually go over a program that you can download to do these equations. We'll talk about cross-sections, the data in the chart of the nuclides, and how we can use this information to determine isotope production. Then when we look at natural radioactive isotopes, we'll explore those, and particularly we'll discuss dating, how one can determine the age of material through relationships between parent and daughter.
A common utilization of the equations we discussed would be describing parent-daughter decay. Here we have an example of a decay chain, the uranium-238 decay chain, in which uranium-238 goes through decays, either alpha or beta, and winds up going all the way to lead-206. There's the uranium-238 series, the uranium-235 series, and the thorium-232 series. These are designated by either 4N, 4N plus 2, or 4N plus 3. For example, if I were to N is divisible by any integer in which we can describe these. The thorium-232 is the 4N, the 238 is the 4N plus 2 series. We can all the numbers are some factor of 4N plus 2, since we either decay by beta, in which A does not change, or alpha, in which A changes by 4. In these decay series, the rate of parent formation, parent goes to daughter, so the rate of the daughter formation is dependent upon the parent decay rate. So example, uranium-238, the formation of thorium-234, the decay of uranium-238 is going to create thorium-234, but then the thorium-234 is going to disappear with a half-life of 24 days. So there's also going to be a rate that's going to be converting the daughter into granddaughter, great-granddaughter, etc. The equations we discussed should be used as the basis for evaluating these sorts of interactions. And so let's take the very simple case. Let's not go into the entire decay chain first, but let's just think about a parent-daughter relationship. So how does the daughter isotope change with parent decay? We already described this. We showed that there's a rate of change where this would be the formation of the daughter, because it's the decay of the parent, and this is the decay of the daughter. So the change of the daughter, which we're going to designate as 2, so N2, is just going to be equal to the rate of daughter formation minus the rate of daughter disappearance, or daughter decay. We can take this equation, rearrange it into what's listed here. We solve and substitute for N using for N1, so the number of parents is equal to the number of parents at time C equals the initial E to the minus lambda T. We get this equation. We solve this linear first order differential by integrating factors, so let's multiply by this term, and we wind up with an equation that's listed here. Okay, so now we have something that we can work with. Let's take this equation and we're going to integrate it from time 0 to time t. We wind up with an expression that's shown here, which is nothing more, it's composed of nothing more than the amount of parent, the decay constant of the parent, decay constant of the daughter, and the time. We multiplied this equation from here by e to the minus lambda 2t, and we solve for n2. So we take this, and this is what our equation winds up becoming. The amount of n2 is equal to the decay constants and the number of parent-daughter decay constants, and then the amount of daughter that's present. And we have two components. This is growth of daughter from the parent, and this is any initial daughter. And I do want to point out that this is lambda subscript 2 for this term. On the previous slide, we showed the relationship to solve for the number of atoms of daughter, N2. Well, by using activity equals lambda n, we can now use the same equation to solve for the activity of the daughter, and all we're doing is multiplying the term that we got by lambda 2 here, and then we just talk about the initial activity of the daughter. One useful equation that we can utilize with this is to determine when the maximum daughter activity has been reached. There's a relationship between the half-lives, the decay constants of the parent and daughter, which tells us we'll reach a point where we won't be making, in relative terms, any more daughter. The decay rate of formation, and the rate of decay will have equaled out. And we can determine this by just finding where the derivative is equal to 0. So that'll be our maximum. So let's solve this equation for t. We get the natural log of a ratio of the daughter and parent decay constants divided by the difference between the daughter and parent decay constant. We can apply this as an example. Imagine that we have a radioisotope generator where we're making technetium-99m. This decays from a molybdenum 99 parent that has a half-life of 2.7 days. The technetium daughter has a half-life of 6 hours. Find the time that's needed so that we have a maximum daughter activity. I'll take this equation, put in these constants, solve, and it comes out to be about a day. So this says that if I have a technetium-99m generator, after I use it once, if I wait a day, I'll reach a maximum activity where I can elute some more technetium-99m off the generator. Right, there are other ways that we can kind of simplify these half-life relationships, and these are really based upon the differences in the half-life between the parent and the daughter. The simplest case is that there is no daughter activity. The daughter does not decay. We just have a very simple equation where the number of atoms of the daughter is just equal to the parent initial 1 minus e to the minus lambda t. This is, remember, showing how many atoms are decaying. Now let's say that we have a radioactive daughter. There's few ways of looking at this. We can look at the relationship between the parent-daughter decay constants and see if equilibrium is ever reached. The first case is that there would be no equilibrium. So the parent is shorter lived than the daughter. So in this case, imagine you have a parent that's a millisecond and a daughter that's a year. During this period, no equilibrium is reached at any time. All the parents decay, then decay is based upon the daughter. Now let's go to a case where the parent half-life is greater than the daughter half-life. And this is if it's around 10 times the difference, it's something called transient equilibrium. In this case, the parent-to-daughter ratio becomes constant over time. As shown in this figure, here are two isotopes, a parent and a parent and a daughter undergoing transient equilibrium, transient because it's changing. The slopes are the same, the total activity is decreasing. What this usually means is that the parent half-life is relatively short compared to the time of our observation. In other words, it's on that same order. So if we're observing it for hours, let's say in this case, this figure, 15 hours at the end, the parent half-life has got to be on the order of hours. It could be 30, 40 hours, but there will be some significant decay during the observation time. We can take our equation, we make a simplification here. We know that n, the number of initial parent, e to the minus lambda t, well, that's just equal to n at any given time t. So this relationship we can use to substitute into this equation. So this equation then becomes this equation, and we see that we have this ratio of daughter to parent is just equal to a ratio of the decay constants, and that's shown up here. Now there's another relationship, secular equilibrium, where the parent half-life is much longer than the daughter half-life. So let's say on the order of 1 times 10 to the 4th times greater. So the daughter decay constant is much, much greater than the parent decay constant. In this case, the parent does not measurably decrease in activity over the measured time. See, we have a pretty constant amount of parent. And what this means is that the activity of the parent and the activity of the daughter are going to be based on each other. So here's our total activity, and the activity of the parent is here, and the daughter grows in and has the same activity. So imagine if this was a case where the parent half-life was 1,000 years, the daughter half-life was a millisecond. So pretty much every time the parent decayed, the daughter would also decay. So the decay rate of the daughter would really be dependent upon the decay rate of the parent. And we see these equations here where the number of, this is from the transient equilibrium equation we solve for. Well, we say that the decay constant times, we use this, so we just say, well, a large number 2 minus a small number lambda 1 is just going to be equal to lambda 2. So this equation simplifies to what is shown here, and we can just say that the activities are equal, and that is shown in the figure above. Now we can add a granddaughter to the decay scheme and try to figure out routes to calculate parent, daughter, granddaughter. One route that's used for this is something called the Bateman solution, the Bateman equation. And we fundamentally have to solve this equation where the granddaughter, N3, well, that's equal to the production of the granddaughter from the decay of the parent minus the decay of the granddaughter. Now for the Bateman solution, we have the number of, this could be n equal 3, granddaughter, 4, great-granddaughter, etc. It's equal to this expanded equation where these coefficients, C1, they're equal to functions of the decay constants and the amount of parent present initially. That's one of the limitations of the Bateman equation, is that these factors only include the parent present, so it only assumes that the parent is present in time 0. There's a link listed here for a program that actually solves the Bateman equation. It has a database where you can put in any isotope you want, and then any successive decays will come from that. You can set a figure to calculate for any time you're interested in, and it'll show the data graphically, and it'll also provide a table of the resulting data. You can download this program and work with the Bateman equation through this.
The ERG nuclide program is currently being upgraded. I found the old version 2.0.0.2. It's available from the lecture link listed here, and it's in the web link part of this page, and it says ERG nuclide 2002 local download. And if you click on this, you'll be able to get the program and install it onto your computer. We'll use the ERG program, as we discussed on the previous slide and gave the web page for, to show the decay of radium-225 to bismuth-209. We'll do this, we'll go through this as an example, and you can use this for any isotope chain that's available. We select the chemical symbol, so we'll do with radium. Select radium, the mass, 225. Out comes all the information, the isotope information. Excuse me, that's 215. Let's go over to 225. There we go. 14.9 day half-life. The decay of radium-225 to actinium all the way to bismuth-209 is listed here. This table gives us information about the radionuclide, its half-life, its yield, in other words, its branching. You see that we have two. From the chain, we see that there are two branches, but they're both practically 100%. The half-life, everything including stable to microseconds, and the initial. The initial is fundamentally here just listed as a percentage, so it's 100 would be initial, as that's the total number of radium-225 atoms we're going to start off with. As we can see, we can input other atoms. And the source, we can also use a activity as an initial source. Here we see the decay chain going from radium to bismuth. You can blow that up and expand upon it a little bit. You see the decay of radium going to actinium, following the chain all the way down to bismuth. So we can take this and set up our settings. We say we want 4,000 hours. So we'll take the unit as hours. It's already selected. The number of steps, we can go up to 1,000 is the maximum, so we'll take 1,000 steps. The step time, we want 4,000, so it's 4 hours per step. We have the total number of atoms. We save that, and all we do is click this little calculator, and it'll calculate the decay. By clicking here, we can show the figure where we see the decay of radium, the growth of actinium, the growth a little bit of some of the other daughters, and then the final growth of the bismuth. If we wanted to have the data itself, we can export the data, and over here we can actually show all the data. So as a function of time, we get the relative concentration of all the isotopes. So if we pick 100, it doesn't matter what we're interested in calculating. We can just use this as relative amounts. We can readily do another example. We'll clear the data. We'll select yttrium 95. There's the decay of yttrium 95 to stable bismuth 95. We'll tell it to calculate it over the same conditions. So remember, 4,000 hours. Here's our growth and decay. See, this one's a little bit more complicated. We see the decay of the yttrium very quickly. The growth of the zirconium, the niobium, and then of the molybdenum. We can see that right here. We can pull up the data. And again, we see that the yttrium, since it's a 4-hour break quickly decays away, and over time we're left with just zirconium, niobium, and molybdenum. This program can be used for any decay chain that's in the database and will probably show up on an exam.
Not all isotopes decay directly from a parent to one daughter. As we explored already with bismuth-212, there's branching decays, and we can use this this branching information and the equations we've already discussed to figure out something about the half-lives of the different decay routes. Now, as we've shown in our data table, in the table of the isotopes when they're given, or in the chart of the nuclides, they only have one half-life. Now that half-life, we use that to determine the decay constant, and that decay constant is actually equal to the sum of the decay constants for all the methods of radioactive decay. Now, since isotopes often just have one primary decay route, it works out that the half-life is equal to the half-life, or the decay constant is equal to the decay constant of a specific decay route. But as we've shown in bismuth-212, there are certain isotopes that have branching where they're both observable. If we have a branching ratio, all that is just based upon the relative decay constants. So any branching ratio, if I know the percentage of the branching ratio, or the relative intensity, all that is just equal to the ratio of these decay constants. So in case of the bismuth-212, the decay constant for the beta divided by the decay constant of the total is equal to the branching of the beta. The decay constant of the alpha divided by the total decay constant is equal to the branching of the alpha. So let's use that to solve for the different half-lives in bismuth-212 based upon the decay routes. We already talked about this equation where the total decay constant is just equal to the sum of the actual decay constants. So for bismuth-212, we have the total decay constant is equal to the decay constant of alpha plus the decay constant of beta. Our branching ratio, the decay constant of whatever route, divided by the total decay constant, is our branching ratio. So for bismuth-212, we have what's the half-life of each decay mode. The alpha branch is 36% and the beta branch is 64%. The total half-life is about an hour. So the decay constant of this is listed here, 0.0114 inverse minutes. Let's use our branching ratio equation right here to solve. So 0.36 is equal to the alpha decay constant divided by the total decay constant. 0.36 is equal to the alpha decay constant divided by 0.0114 inverse minutes. We use this to solve, and this becomes the decay constant for alpha is 0.0041 inverse minutes, and the alpha half-life is about 170 minutes. Then if I use the equation that the total decay constant is equal to the alpha plus the beta decay constants, well, I know the total, I know alpha, I can now solve for beta, and the decay constant, or the half-life for beta, works out to be about 100 minutes. One utility of all these equations is to evaluate radionuclide activity, or dose, over a period of time. And here's an example of of a summation curve of different elements from radioactive waste. This is how their activities, and those activities are actually converted into dose, how they change as a function of time. You can see that this is a somewhat complicated figure. There's decays, there's some growth followed by decay. So neptunium increases, then goes down, americium increases, then go down, then plutonium decreases and decreases differently because of the different isotopes. So we can take very complicated systems and just exploiting the equations we've discussed, come up with a figure that we can explain some behavior for radioactive waste over millions of years. Let's expand our calculations and equations that we're going to talk about in this section to include cross-sections. We've already explored on the chart of the nuclides, cross-section data for neutron reactions with isotopes. So we've already presented the cross-section. Now let's start utilizing it. The cross-section is fundamentally a probability. And it's a probability for some reaction occurring as we looked at different isotopes, different reactions on those isotopes, or one isotope compared to the other had different cross-sections, which just meant that the probability of that reaction occurring varies. And when we talk about nuclear reactions, we'll go into more detail on why those cross-sections change. The value for a cross-section is an area value. And this originates, this term comes from the probability of a particle hitting a nucleus. And nominally, you would say that the probability is just based upon, well, how big is your nucleus? So these dimensions, these areas, are on the size of nuclei. For fast neutrons, total cross sections are on the order of 1 barn, and a barn, as we already talked about, is 10 to the minus 24 centimeters squared. And you need to remember this number if you want to utilize it in an equation. So the cross-section units are in barns, and the barns are 10 to the minus 24 centimeters squared. And that actually comes from the nuclear radius being about 10 to the minus 14 meters squared. Cross-sections can be used to determine the rate of formation of the products from the reactions. There are 2 equations that are listed here. One is for accelerators, and one is for a target in a neutron flux. So for the accelerators, we have the rate is equal to the incident number of particles per unit time, the number of nuclei per centimeter cubed, the target thickness in centimeters, so now this unit becomes centimeters squared, and then the cross-section. So these terms are related to an accelerator. If I give you an incident particle flux per unit time, that's usually a current, so that's particles per second, you can get the formation rate per second of the products from that reaction. For a target in a neutron flux or in a reactor, the equation is a little different. The rate is the same. We're looking at some process per unit time, so particles formed or atoms formed, nuclei formed per second. But the data we have is our cross-section, which we've already explored these cross-sections in the chart of the nuclides. The flux, that's how many neutrons per centimeter squared per second, and the number of nuclei that are in the target. We can get this from the mass. All right. So we have 2 primary equations, and we can utilize some examples, and we're going to focus primarily on the reactor examples. Now there's also something else we need to consider, is the product nuclei that's formed. If it's radioactive, we need to consider its half-life in terms of the total radiation time. If something's radioactive, as it's being made, it's also decaying. So there reaches a point where we have some saturation factor. This term here is listed as our saturation factor. That's the maximum level that can be reached. And if we know something about the activity, here are the saturation factors. This is what it looks like as a function of half-life. So this tells us something about how many half-lives we should really irradiate a sample before we start losing the benefit. If we irradiate a sample for over 5 half-lives, we've basically saturated and we're not going to be making any more new isotope if we're irradiating for more than 5 half-lives of that isotope. If I know something like the activity at the end of a bombardment, and I divide that by my saturation factor, I can actually use it to calculate the total rate of formation of that product. So that's similar to the equations that we showed on the previous page. Let's do some calculations. Let's start off with something fairly straightforward. Let's say that the irradiation is short compared to the half-life of the product isotope we've made. And in this case, let's find the amount of iron 59 that we make from irradiating 1 gram of iron in a neutron flux of 1 times 10 to the 13th neutrons per centimeter squared per second for 1 hour. So the half-life is 44 days, and we're going to radiate for an hour. So the irradiation time is short compared to the half-life. This is our nuclear reaction. We have iron 59 adding a neutron, iron 58 plus a neutron going to iron 59. We look up the cross-section for that reaction. It's 1.3 barns, so that's 1.3 times 10 to the minus 24 centimeters squared. The number of iron 58 atoms that we have, we said we had 1 gram of iron. Here's the molecular mass of iron. Multiply that by Avogadro's number. And this value here, that is the percentage of iron, that is iron 58. So now here's our total amount of iron 58. Let's utilize this equation. Our simplified rate is equal to the flux times the number of target atoms times the cross-section. And if we do that, we see, we just plug this in, we have about 3.9 times 10 to the 8th atoms per second in 1 hour. That would give us 1.4 times 10 to the 12th atoms produced in 1 hour. And so this does not account for the saturation factor, does not account for the decay of the iron 59. Now let's do the full expression where we utilize this equation, which accounts for the decay of the iron 59. And the terms we need here are the cross-section, the flux, the initial amount of target, the decay constants, and the total time. So we see here's the total time, 3,600 seconds. We said we're going to radiate it for 1 hour. Our decay constants, and then the other data that comes from this equation. We input those terms, we solve, and we see that the difference between the two is very small. 1.423 versus 1.422 times 10 to the 12th atoms of iron 59. So in this case, we could say that not accounting for the decay has not a big perturbation on the variations in the answers utilizing either equation. Let's take a different case where we have the half-life and the irradiation are on the same order. So let's say the amount of manganese 56 with a half-life of 2.5 hours from irradiation of 1 gram of manganese in a neutron flux, same, for 1 hour. Okay, manganese 55 plus a neutron goes to manganese 56. That cross-section is 13.3 barns, so the cross-section is 13.3 times 10 to the minus 24 centimeters squared. manganese 55, 100% of manganese is manganese 55, so we use this molar mass times Avogadro's number. That gives us the number of target atoms. Now let's plug this one in to our simplified equation here. We get atoms per second, 3,600 seconds in an hour. We say that we make 5.2 times 10 to the 15th atoms of the manganese 56 in 1 hour. This equation does not count for decay. Let's do the fuller equation where we do account for decay, put in all our terms, and we see that the result varies. And this makes sense because we're radiating for an hour. The half-life is 2.5 hours. During that hour of irradiation, the manganese is decaying. So in this case, we certainly need to use this equation to get a reasonable calculation for what we would actually observe. As we mentioned earlier, we can actually get the formation rate from the activity. So let's use our previous examples and use the equation that we've already discussed, where the activity divided by the saturation factor gives us the formation rate. If in our previous example we made 4.6 times 10 to the 15th atoms of manganese 56, the activity of that would be equal to lambda n. Well, we have n here. We plug in our lambda. This is our activity. We take that activity divided by the saturation factor, and we get 1.45 times 10 to the 12th atoms per second, which was equal to the rate of formation in the simplified equation. The equations that we discussed are useful in radioactive dating. It's actually one of the wide applications of these equations. For isotopes that are in the environment, we can use their changes and their decays from parent to daughter to figure out how long samples that contain those isotopes have been in the environment. And we can think of two types of isotopes that are available. There's primordial radionuclides with long half-lives that have been around since the formation of Earth. And then there's shorter isotopes, such as carbon-14, which are continuously produced by interactions of matter with cosmic rays. There are also some anthropogenic radionuclides that have been introduced since the initiation of weapons testing. So fundamentally, dating just works as a clock. And all I'm doing is solving the number of atoms at times t is equal to the number of initial atoms, e to the minus lambda t. If all I have to know is the number of initial atoms, the number of atoms at time t, and I can solve for t. So obviously nt I can measure because we're at time t. What I don't know is the number of atoms that are initially present. If I make the assumption that if the parent that are present at time t and the daughter that are present at time t, well, that total amount must be equal to the parent initial. So if I have one isotope decaying from one parent to one daughter, if I measure it at time t, so if I measure it currently, that sum must equal to the parent that was initially present. Now, the assumptions for this dating means that there are no daughter atoms present at time t, that all the daughter is due to the parent decay, and that no daughter was lost during time t. They actually have routes for evaluating this and determining that this is true. For instance, not only can they measure the parent and the daughter, but you can also measure helium that's formed. Helium's formed during the alpha decay. So for instance, if we have uranium-238 decaying to lead-206, we produce a number of alpha particles. If in those samples the helium is present, if that sample locks in the helium, it's a very good bet that it would lock in the daughter also. So we utilize this equation. It becomes that the time, or the date, the age of a certain sample is equal to the inverse of the decay constant of the isotope that we're evaluating, divided times this term where we're dividing the daughter at times t and the parent at times t. So two terms that we can evaluate. For as an example, imagine that we have a mineral and we evaluate the ratio of uranium-238 and lead-206. Now this decay occurs through a number of different isotopes, but fundamentally the half-lives between uranium-238 and the stable lead-206 are short compared to the uranium-238, so we can just take it as a single decay step with the half-life of the uranium-238. That's 4.5 billion years. I can take a sample, measure this ratio, and then you can state what's the age of the mineral. I plug my terms into here, and I get 2.2 billion years. And this route is actually used for measuring very old samples. Another well-known form of dating is carbon dating, and this is based upon the fact that there's constant formation of carbon-14 in our environment. If anything is living, it's taking up carbon with a certain amount of carbon-14. When it is no longer living, it is no longer taking up carbon-14, so the carbon-14 is decaying. We utilize this fundamental equation where in the sample we get some sort of relative amount of carbon-14 in the sample, and we compare that to the equilibrium amount. At equilibrium, there's 227 becquerel of carbon-14 per kilogram of carbon. So if we take a sample and we measure the relative activity per unit mass of carbon, we can calculate its age. So if there's a wooden sample with 0.15 becquerel per gram carbon, so as opposed to kilogram, 3 orders of magnitude, so this would be 150 becquerel per kilogram. What would be the age of that sample? So 1 divided by the decay constant times the log of the ratio. We plug this in and we get a sample of thousands of years. Now carbon-14 is good for measuring decay constants on the order of thousands of years, and as we saw with uranium-238, it's good for measuring that decay constant is for measuring on the order of billions of years. So the dating method does work best based upon the isotopes, half-lives, and decay constants that you're utilizing. Right, we can utilize these equations and set up some relationships to determine something about the Oklo reactors. You may have read about this in the beginning of the book, the table of the isotopes, that a couple billion years ago there were natural reactors based upon formations of uranium minerals that were critical in Gabon, present-day Gabon. We can utilize our equations to evaluate when this occurred. So let's just explore an equation where we say, let's compare the ratio of uranium-235 to uranium-238 and use this fundamental equation. The ratios I'm going to base upon the fact that today the 235 is 0.7% of the uranium. For a reactor, about 3.5% of the uranium needs to be 235 in order for the reactor to go critical. So we're going to base this assumption on saying we need to figure out what was the time when uranium-235 was 3.5% of the uranium, knowing that it's 0.7% today. So this would be the ratio that we'll look at. Those ratios are based upon the percentages. So the ratio of uranium today is equal to this ratio initial times this ratio of the decay constants and half-lives. the equation just becomes here. Now let's rearrange this equation, solve for t. We're doing that here. We get this equation where the time, the date that this occurred, is equal to this ratio of 235 to 238 today divided by the ratio of 235 to 238 initially. We're getting those factors from these percentages divided by just some differences between the decay constants. So it's a fairly straightforward reaction. We input these values, and remember this isn't a percentage. This would be 0.7 divided by 99.3, and this would be 3.5 for the percentage of the uranium-235 divided by 96.5. If we do that, we get an answer of about 2 billion years, which is roughly the order of the time for the Oklo reactors. All right, both these lectures, we utilized basic equations. We had relationship between half-life and lifetime, count and error. Those were primarily in the first lectures. The second lecture that we just listened to, we utilize equations for mixtures, equilibrium, and branching, cross-sections, and dating. You should be able to answer questions that are listed here. How can we evaluate half-life, define Curie and Becquerel? What's the half-life for each decay mode for the isotope of bismuth-212? We did that example. Determine the amount of cobalt-60 produced from exposure of 1 gram of cobalt metal to a neutron flux of 10 to the 14th neutrons per centimeter squared per second for 300 seconds. This would be an example. And what are some basic assumptions in using radionuclides for dating?
As a final note, the data and equations that we just went over in both these lectures can be used for some good projects. If you're going to be doing more work in radiochemistry, you can make Excel spreadsheets. They can be used to calculate, for instance, mass or mole from activity, the concentration and volume to activity. So if I have a certain volume, 50 milliliters of a certain uranium solution, I can calculate the activity of that solution. This information is often needed for utilizing radionuclide solutions or solids. You can also talk about isotope production from irradiation based upon a certain reactor, or parent decay from parent to daughter to granddaughter. When these, what we just discussed, are not assigned, they're just ideas. But what is necessary is that you comment in the blog and respond to the PDF quiz for this lecture.